So, Jonek, slide is visible.
Yeah, yeah.
So, good evening, student. Uh, so I will start the today's live session 2 class on that week 2 assignment, and if you have any issue during that lecture of that course chapter 2. So we have new TA also, that Jonek Navi Sharma is from NPTEL team side from TA. So he will be also help in your doubt, and also you can ask to him also that doubt. So Jonek, can you introduce yourself?
Yeah, I'm doing MTech in IIT Madras under Department itself. So, like, I just did this course 1 semester ago. So, I hope I can help you guys. But I only know slightly more than you guys. That's it. But anytime you have doubts and I cannot solve those, I can escalate to ma'am anyway. And guys, please use the discussion forum that is available in the NPTEL. Like, it will direct you towards the Google group, I think. But post questions, we will always try to answer them. Okay.
So
Uh,
you can also post your query on ask to question also, so we can reply there also your doubt here.
yeah. And
So
this,
Jonek have
uh,
previous experience on this fiber optical communication technology. If I am not possible from my side, then he will answer your questions. So I again expect from your participant, from your side, student. So we are happy to answer your all the questions. So these are the I have got the classroom doubt. One is from Sania Azim. So he talk about that Lambertian. What is the Lambertian in this pattern, and how we can get that about that? He have doubt. So basically, Sania, are you there in the class? Sania, are you here? So this is the like that radiation graph you have seen in that microwave also, that to calculate the reflection constant and transmission constant, like that polar plot, maybe you read in your microwave. So in optics, Lambert's quotient law say that the radiation intensity or luminous intensity observed from an ideally diffuse reflected surface or directly proportional to the cosine of the angle theta. So
let me do a recap, and
yes,
you can discuss the questions right after that. I'll just do that. Let
what
me
Janek?
present. Let me present.
Okay, okay,
We can discuss the questions right after we have a quick recap of what is
okay,
it.
okay.
Sir, I have only one minor question. Can I ask right now?
Yes,
Yeah,
yes,
yeah,
tell.
sure.
I'm talking about practical case. Like we have a single optical fiber, or it is having. I'm taking it. It is having a carrier frequency of 10 to the power 13 to 10 to the power 16. I'm taking 10 to the power 16 hertz. So how many voice signals can be transmitted in a single optical fiber?
Um, so we will multiplex a lot of. We can multiplex a lot of channels. You can imagine.
So I just
Currently,
want to know
BSNL.
this. So
How many?
I am calculating like we have a carrier frequency of optical fiber 10 to the power 13, 10 to the power 16. I am taking as in 10 to the power 16 hertz, and I am dividing this frequency with our voice signal frequency. Voice signal is 3.4 hertz to 34 kilohertz. So I am calculating approximately 10 to the power 9 signals can be transmitted at a time.
But
I don't know practically it is feasible or
but
not.
so at 3.4 gigahertz, you will have cellular signals also, right? Or radio at some megahertz ranges. So when you say at optical frequency of some terahertz, you cannot transmit something from zero to that value in the entire band, right? You will pick a small bandwidth that the government will allow you. So you cannot take up the
Many signals
entire
can be
bandwidth that is
transmitted.
you will divide it up into multiple channels using some time division multiplexing or frequency division multiplexing. In optical domain, we talk about wavelength division multiplexing, right? WDM, a term you might be hearing. So,
Yes, sir.
like you want to able to use the entire however many terahertz you have. Right now, BSNL, you can take an example. They are offering
Mm-hmm.
channels of around 100 GB, yeah, 100 Gbps. 100, yeah, 100 Gbps. Uh, that is to be converted to this small channel, but like they won't be like wide channels. They will be like at max it will be 10 nanometer or something. If you're transmitting at 1550 nanometers, one of your channels will be like 1010 nanometers. The numbers are, don't take these numbers seriously, but I have to calculate again. But like um,
So, sir, how many signals can be transmitted in a single optical fiber? I used to say like 1 gigahertz signal can be transmitted in a single optical fiber.
yeah,
Okay, sir.
uh, let me check, recheck the numbers and post in the discussion forum. Okay, because I have not calculated
Okay,
the
sir.
numbers. So let me
Okay, sir.
get back to you. Okay.
Okay, sir. Okay, sir. Thank you so much, sir. Thank you, sir.
So Janek, you want to continue?
Yeah. Wait. Okay. I hope it is visible.
Yes, yes. This is visible.
Anyway, I have not. I'm not discussing week one contents, but week one's assignments. Assignment is also due tomorrow. So if you have any doubts, you can ask today itself. If some question is not
You
clear,
can ask the
we can.
doubt at the end of the session, no?
Yeah, yeah, yeah.
No, no. In the
Okay, sir.
assignment, if you
Okay,
have
sir.
any doubt,
Yes, sir. I have one doubt.
you can ask that.
Anyway,
So I'm just
yeah.
having doubt in highest spectral efficiency. Like I'm calculating the spectral efficiency for 16 QAM, having a bit rate of I think 16 QM, having a bit rate of 10 baud rate. And so I'm getting the spectral efficiency of each of them same, 2 bits per second per hertz.
Yeah, that's fine, right? How many bits are you sending per symbol?
So
So,
just I think it is question number, yes, yes, sir. It is question number.
It is four.
Um, no, sir, no, not this one. It's question number six, sir. In question number
Okay,
six,
okay.
I'm having doubt.
Which one of the following has the highest spectral efficiency at Nyquist sampling rate?
Yes, sir. So I
so
got the bit rate of for first one I got the bit rate of 40 Gbps. For the
Okay.
second I got the bit rate of 80 Gbps. Next one I got the bit rate of 64 Gbps, and for the next one I got the bit rate of 160 Gbps.
So,
Okay.
see, these are graded assignments, so I won't answer directly, but
Yes, sir.
you're on the right track. Okay.
So just tell me one thing. For the
Yeah.
Nyquist sampling rate, I have to take the FS only, na? I don't have to take two of FS for this
No, no,
because
it's
it
fine.
is saying
Yeah.
at. Okay, sir. Okay, sir.
Okay.
Okay, sir.
Anyway, this week we started the transmitter part of this.
So,
Yeah. Go ahead.
yes, I have a doubt in one of the topics. So, actually, I'm unable to understand the relationship between full width, half maximum, and the spectral width. That's what is this?
Full
It's
with.
not a spectral
Uh,
width exactly. It's that PF, sir. Mu F, yes, that term. The relation between FWHM and mu F, because there was one of the questions in in our lectures that how are they dependent and the that FSRs and how it is affecting the single longitudinal modes. So I have a bit of confusion
Yeah, right, right.
in their relationship.
Um, so basically, full width half maximum of some. So basically, full width at half maximum gives uh, the if you plot intensity versus frequency, so it will give the width when the intensity is 3 dB down from the uh, peak value. That is the definition of full width at half maximum, because the intensity is half of the maximum value, right? And FSR is a uh, just a metric that we use to uh, describe the separation between these peaks. For example, FSR in this case will be higher, and if these peaks are blending together, so ultimately you will see something like this where the extension is not good. So uh, FSR reflects on that. I think we have already posted this question in discussion forum. So let me answer in more detail in the discussion forum. Okay, I'll get back to you before, like, I'll look it up once more, then get back to
Okay,
you. Okay.
so
So FSR, don't
so
think too deeply into it. It's just a metric that we use. It's widely used metric, but uh, okay.
Sir, excuse me,
Yeah.
sir. Sir, can we come to a conclusion that spectral width will be equal to twice of full width at half maximum?
Yes, spectral width is defined like that, right? By definition.
No, sir. Like you have said that full width at half maximum is nothing but the 1/2 times of
Yeah.
the peak point, right? So
Yeah.
can we come to a conclusion that spectral width is nothing but it will be equal to twice of full width at half maximum?
Yeah, you can say that. For example, in for LED phase, we have something like this, right? The uh, frequency versus intensity. So, if spectral width, when we say spectral width of an LED is 11 terahertz, we mean this full width at half maximum is 11 terahertz.
Sir,
Okay,
then spectral width will be equal to how much, sir?
full width half maximum, we can say. What is the actual
Spectral.
spectral width? But when does any non-zero value starts for this distribution? It goes up to infinity, right? E to the power minus something it comes. H mu minus. Yeah,
Then spectral width is nothing but full width at half maximum, sir.
yeah,
Or
yeah. That's how we describe the spectral width.
It is a spacing between two consecutive cycle, maybe, Jonak. Like,
so sir, can we say that the longitudinal mode of the laser will get better if we increase the full width half maximum?
We want smaller full width half maximum, yes.
Yes, sir.
Uh, we like when uh, the emission spectrum of the light source itself is very sharp at one frequency. For example, we use lasers at 1550 nanometers these days, and we want this to be very narrow. We
Yes.
will when we modulate some signal on top of it, it will
Mm.
occupy some more bandwidth. What
Okay.
Namita is asking is this how much total bandwidth it will occupy. It will depend on the data rate also. But right now we are not talking about it. Okay.
Okay, sir.
So these will interact, but ideally we want the source line width to say line width to be as small as possible.
Okay. Okay, sir, got it.
Let me see. So basically we started with LED. These are just the video titles you can see. Uh, we started our discussion on the transmitters that we use generally. LED is useful because it introduces us to a lot of concepts, and also sometimes we don't need lasers because lasers are expensive. Communication grade lasers will cost you above 1 lakh. Okay, LEDs are very cheap because they are mass produced in England, and so LED will operate and under the principle of continuous emission, and these are basically the topics we have covered this week. Um,
So can you share this PPTs also with us? Actually, you just summarize all the formulas at a single place. So I think it would be easier for us to remember all the formulas at the time of exam.
okay, I'll ask them first. Okay. So these are all the formulae that were introduced in this week. Okay.
Yes, sir. Yes, sir.
We
So
started
that's why
with
I'm asking
LED.
if you
Yeah.
are able to share all these slides, and it would be benefit for us at the time of exam. We can revise it thoroughly.
Yeah, but also
Namita, this
you
will
should be
be.
making these yourself also, right? I'll ask ma'am anyway, but
Okay, sir.
you should be
Okay, sir.
making
Okay,
these
sir.
yourself. Like
No,
you can
Namita, you
keep
can
this.
see on the YouTube channel also. We have record this and upload on the YouTube channel also. This
Okay, sir. Okay, I'll check on that, sir.
from Fiber Optical Communication Technology YouTube channel. You can got this, these things also. That if you no one will be joined, then he can later can see these things.
Okay, sir. Thank you so much, sir.
These are just the formula that we use, um, and all of the assignment questions can be solved using these formulas. These are all covered in the videos. And just
Joining
take notes
either you
and
can
you'll
post
go.
these three slide on that Google Classroom also. That
Yeah, sure, sure.
yes.
And towards the end of the week, we also started on resonator concept that will be useful for lasers, of course. And um, also, during some of the assignments, you'll be asked to use MATLAB to run some code and make changes in the code. So please try to use the MATLAB licenses that NPTEL has purchased for you. Okay. MATLAB you can use online also. That will look something like this. You can run it from browser, and NPTEL has purchased these licenses during for the duration of the course. Okay. Um, please try to get familiarized with MATLAB because it will be useful. So, for example, if you just want to try to plot out this uh, continuous emission intensity versus frequency graph, the formula you have, uh, the formula is here given, and you can try plotting it, and you can see how this plot actually behaves. Like you can calculate full width and half width from the plot itself. So please try using MATLAB. NPTEL has like paid a lot of money to get this. And I also wanted to show a typical LED. This emits at 780 nanometer, and E means some epoxy uh, placing has been used on the LED. LED part is just the middle part of it. The LED part is very small, and you can see typical values For example, full width at half maximum is given as 13 nanometers. You can convert it to frequency also. Um, because frequency values are so high, optical people usually like specifying things in wavelength. That's why you hear wavelength division multiplexing. That is just frequency division multiplexing, but the numbers are more tractable when we are using this um, wavelength figures. And intensity versus wavelength it has plotted. In class, we have discussed intensity versus frequency, and the intensity versus angle, the pattern of emission that is shown here. These are typical values you can expect from a data sheet in order to use a LED. And, and basically, example questions. So, given some values, you can get some other values. I think Ashok has done more regarding this. I'll hand over to Ashok.
So Jonek, they have any assignment on MATLAB, any program or they have to do?
In week 5, we have one question. Uh, it will leave you enough time to have the MATLAB code running, but then you have to change some values in text. So you'll be solving some transcendental equations where the value you want is on both sides of the equation, and they can be decoupled and things.
So
So
I request all the students be familiar with the MATLAB for your assignment and for your practice also. And during in MATLAB usage, if you have find any difficulty, so you can post us so we can help you in these things also. Right, Jonek?
yeah, and we can definitely show some basics if you want.
Yes, yes. If you
Hello.
need,
Yes, please go ahead, Jagannath.
if you need any help in basic and with familiar, then next week we can arrange for that also. It's right, Jonek?
Yeah, yeah.
કે બુજી કહ્યું
Yes,
નોડલ કહું તું નોડલ કરતો
Nayak.
Yeah, Manish this side. Can you please share some kind of demos to, familiar with the MATLAB? Basic understanding.
યસ
Yes, Manish, we can
sir, we need
schedule
to
on the
understand it
next
very
week.
soon.
That will be great help. Thank you.
Okay, so maybe Jonek or I will be both of you will arrange for one you for that half an hour session. Jonek, it is right?
Yeah, yeah, yeah. We
Yeah,
can do
absolutely.
this time
Post that we
also.
can do some kind of assignment and problem solving over there. No?
Yeah, you can go through also YouTube channel for familiar also. There is many video on YouTube channel from IIT professor or some student.
So how
Okay.
can you get the MATLAB and how can you use it?
You have the
Uh,
access on online access through that SWAM portal.
Yes.
NPTEL Fortes is a MATLAB section. Just go through that. Um, Ashok, are you discussing
Yeah.
questions? Example questions?
So we can I present?
Yeah, sure, sure.
Okay. So slide is visible.
Stop presenting once. It
Again I
becomes
have to
meaningless
present.
because I was presenting.
Slide is visible.
Yes.
Hello.
Yes, it is visible.
yes, visible.
So Sunil Prajapati have asked on Google Classroom one question, difference between frontal reflection and total internal reflection. So in the frontal reflection, whatever that there is the two medium of light, like that these questions. So we have an incident light, and it some part will be transmitted and some part will be reflected. Like that, it have reflecting index n1 and n2. So there is a two different dielectric medium have a two different reflective index. So the whole light will be not pass transmitted through that medium, but some part will be reflected. So it will be loss of some data during that frontal reflection. In total internal reflections, the light ray like that move from one medium. It is the same reflecting index n1. It will not move to n2 because its sin theta c is greater than equal to n2 by n1. So this is the difference between the frontal reflection and total internal reflection. Sunil, are you there? Sunil, Jonak, you want to add something here?
Both, like how light reacts when you see
Hello,
a boundary. So Sunil is
Jonak,
not here.
you are not audible proper. Some
My network must have dropped. Yeah, it's okay.
okay. So this is the question asked by the Sunil on the Google Classroom. This is the assignment question we have to discuss. So I need your participation, or if you have any doubt, then I will explain it, or otherwise, anyone can explain these questions. So, question is about the. So, I have some questions. Someone tell me the list of the name of the semiconductor optical source. What type of the optical source we use? Anyone can answer that.
So LED, laser,
Other? Anyone? Anyone else? There are 40 students. So, yes, Namita, there is the LED lasers. So these are the optical source through which we can transmit a signal from optical fiber. For commercial development, the most important parameter for optical communications. What is the most important parameter we consider for the commercial development of the optical communications? So these are the questions from your classroom only. Uh, Madam, I already explained in their lecture. So please,
sir, spectral width,
okay,
um, efficiency,
okay,
um, bandwidth,
okay,
The power consumption,
yeah,
power consumption,
yes, power consumption.
Noise.
Which type of
reliability
noise?
and cost effectiveness.
Which type of noise you consider, Kusagra?
Sir, in transmitter there are different types of noise,
So what types
and
of noise? What types of
like
noise? Can you explain that noise types to
I
the
think
students?
linear noise.
relative
Linear
intensity
is
noise.
not type of the noise, Manish.
Gaussian noises,
Yeah, Gaussian is correct.
thermal noise, amplitude,
What?
Phase noise.
thermal noises,
Okay, phase noise.
amplitude,
Amplitude noise, okay.
Temperature noise.
Okay. Some more noise is like that white noise, flicker noise, short key noise,
thermal noise, short
Johnson,
noise.
Johnson noise. So these are the types of the noise which will affect our signal during the optical communication also. So we will be optimize that also. So we will receive the correct output at the output side of our detector. So anyone tell me the what is the basic principle of the semiconductor source? LED, laser, photodetector.
Laser is population inversion, sir.
What is the population inversion?
So here in laser, we were stimulating an we are using stimulated emission processor so that we are stimulating an photon into the bands, so that because of that the photon will be combined with the, either it might be electrons or with the holes, so that there will be, it will get excited and it will go to the higher excited state. So because of that the total valence band I mean,
Yes, yes, you're right. You are nearby it.
yeah, yeah. So the holes in the valence band will get excited into the conduction band. So most probably all the holes will be excited to the conduction band. So there is a population inversion. Before that, there was, it might be equal in number in between the conduction and valence band. After stimulating an photon, so there is population inversion. So this principle is known as population inversion, sir, as I feel.
Will
Can you?
LED not use population inversion?
Yes, Jonek, your voice is very less.
Okay. LED also requires population inversion, right? You told about laser.
Yes, sir. But here we are stimulating an photon, right? It will be, uh, it will happen within a less period of time. But whereas in LED, it was spontaneous emission, even though it will happen there, but here it will happen in a fraction of seconds.
Yeah,
So
yeah.
LED will be
Dominant
Perfectly.
LED will be
Yes.
working in forward bias or reverse bias.
forward, sir.
Why we are given to forward bias? Any reason?
Because to have electron hole recombination,
So it will take emission
mm,
of the emission of that light. See that if we have the band gap like that, sorry, we have valence band, we have the conduction band. So this is the conduction band, this is the valence band. This is our Fermi level. So this is, maybe we have call it a band gap. This will be band gap is equal to EC minus EV. Energy gap of the conduction band of the energy band of the valence band. Maybe we say that E1 minus E2. It is depend upon you. So whatever that, when light will be focused on that in valence band, this is the material in the valence band. So it will generated electron and hole pair. So electron will move into the conduction band and it will leave the holes in the valence band. So we have the electron here, electron here, electron here. Okay.
So actually, the free electrons combine with the holes and they
It will
produce
combine
the
in bit.
emission actually.
That's why we have given the external biasing to the device.
Yes.
So it will generate a charge carrier injection inside this. So it will responsible for the recombination of hole and carrier, which will take place the emission, not the absorption. It will take the emission. So in the laser we have the population inversion, but it will, in population inversion like that, it will, if the light electron, it electron will create the electron more number of the, when it will not recombine, it will generate more electron. So it will have the continuous of emission like that in a laser. Jonek, right?
Yeah, you need carrier injection to cause a sustain a population inversion.
Yes. So what is the basic principle of the photodetector? Anyone can tell me how photodetector will be work?
so it is used as a receiver.
Yeah,
As a receiver.
we use at the receiver side, but working principle I know that. How it work?
So absorption,
Yes, absorption. So how absorption will be happen?
because it will absorb the light coming from the
Yes.
transmitted section, right?
Okay.
So based on that,
Sir, it
we
has
can say it
N
works
junction.
on the absorption principle.
So when absorption will take place, what happen?
Sir, it has N junction that consumes light energy to produce electric current.
It converts into electrical energy, sir.
No, it will
Exactly.
convert electrical signal. Okay, something. But when some light will be
Electrical
like that,
energy, current.
my photo detector, and when light will be focused on this, what happen in this case?
Sir, it consumes light energy and convert it into electrical energy.
No, it will also generate the electron hole pair, but it will in this case recombination will be not happen. Recombination will be happen in this only in case of the defects.
So will it
So
act as the
Sir,
opposite
it
to LED?
depends upon the material used. No?
every material like that, if the direct band gap material semiconductor or indirect band gap semiconductor, in indirect band gap semiconductor we can directly recombination will be not place, so we cannot use in LED or laser. But in photo detector we can use that indirect band gap semiconductor because we do not need the recombination of that electron and hole pair. If electron and hole pair will be recombined, then it will be work like the LED only. We need only the photon generation. We do not need that case. We need a maximum number of the photon will be generated through that photo detector, whatever the material that we used photo detector for. So absorption will be take place only on that case, and in every where absorption will be in that case of the LED spontaneous emission will take place. So it will create only, it will recombine only electron and hole pair, but it will not generate electron again. But in case of the stimulated emission, one electron will generate another electron, so it will make the chain of the electron, and then it will be
One
recombined.
photon will just,
Yeah.
um, for
Yes.
stimulated emission, one photon will result in multiple photons.
Yes, it will create a change like that in
Photon will,
avalanche mechanism. So, anyone tell me about the primary limitation of the LED?
Sir,
So it is not
wide
functioning
spectral width,
focus wise.
wide
Spectral width is large.
spectral, wide,
It should tell
wide,
us.
wide spectral width.
Bandwidth is
Yes.
And so
restricted, sir.
it is not so it is not easy to couple the light from LED in a single mode fiber.
So, uh, you say that the bandwidth is
Of the value of the
yes, yes, value of.
yes, the TC value is actually means the lifetime for that thing. So actually, I'm not sure. I'm not about this. It has a limited modulation of bandwidth. Sir.
So
Okay.
it can vary with respect to
So in
temperature.
single mode so in single mode fiber it is not feasible to couple the light from LED. But in multi-mode fiber, we can use LED as an source. But for a single mode fiber, we can't use LED as an optical source.
Okay.
So it
And
has a divergence beam actually.
what?
come again. All the previous ones are correct. But, um, anyway, okay.
So, this question is clear from this doubt, this discussion. I think that first question, if you have any doubt, that then they can ask us. So I move forward. So this is the direct and indirect separation, and that for that you. So second question, the most mature SI technology not suitable for manufacturing of the semiconductor source, because why we use not silicon as a for semiconductor source like that LED and laser?
Option
It
C.
does not
Indirect
have
gap.
a direct band gap. It is indirect band gap material.
Why indirect band gap is not suitable for the optical source?
because there will be not be conservation of momentum in the indirect band gap material, so
So
electron hole recombination is not possible.
okay, electron hole combination will be not possible.
Yeah,
Okay.
because there is momentum mismatch.
Okay, and in the direct band gap semiconductor, momentum is preserved, conserved.
Yes.
Yes, momentum and energies are conserved.
So have you any giving me some example of the direct band gap semiconductor material?
Like indium
So
gallium
gallium
arsenide,
arsenide,
Gallium
Gallium
arsenide.
arsenide, sir. Indium
indium
gallium arsenide
phosphate.
also.
Okay. So what is the band gap of the gallium
Gallium
arsenide?
arsenide phosphide.
What is the band gap of the gallium arsenide?
sorry,
Band gap value of the gallium arsenide.
So
1.4 eV,
1.47, 1.47 electron volt.
And silicon?
So
Silicon.
1.2,
1 point?
1.2, I think.
silicon 1.21 at
Okay.
0 Kelvin and 1.1 at 300 Kelvin.
Okay. So what is the we have this many devices are based on the silicon technology. So in other than optical source, where can we use the silicon?
So in the manufacturing of Zener diode,
Okay.
designing of MOSFET devices, we are using silicon only, silicon wafer.
Okay. Can you use as a photo detector silicon?
Yes,
So which wavelength, which light spectrum will be detected by this silicon?
infrared.
No, no, no.
No,
Infrared.
actually, it depends upon the quantum efficiency
No, no.
of the diode.
Have you know the relation between band gap and that wavelength of that? Have you aware about that?
Yes, sir.
What is
Yes,
that?
sir. Wavelength equal to 1.24 divided by band gap, sir.
So band gap of silicon is 1.1 electron volt. Then which wavelength is detected by the silicon? That case, can you calculate that?
Maybe ultraviolet.
Yeah.
Maybe, sir.
How much wavelength will become 1.24 electron volt divided by 1.1?
1.117, sir.
Yes. How, which wavelength will become? How much nanometer?
Even 100.
Yes. How much? 1200.
This is in micrometers, not nanometers.
Yes, Onek.
This will come in nanometers. I mean micrometers, not nanometers.
This formula is valid for my in micrometer. No?
Yeah, yeah,
Yes, it is for micrometer.
So you can calculate nanometer also. That no problem.
yeah, yeah.
It is 10 to the power minus 3 again here.
Approximately
Approximately
1100 nanometers, sir.
1100 nanometer. So
Yes, sir.
it will become in which region? It is visible IR or far IR?
Visible maybe. Because invisible range
Yeah,
is 0.38 to 0.76 micrometer.
Namita, that time I also discussed that. It is from 700 nanometer to 1100 nanometer is a IR range. From 400 nanometer to around 700 nanometer it is visible. From 180 nanometer or 100 nanometer to 400 nanometer it is UV. So it will more suitable
So,
for,
sir, I think it is
yes,
IR and micro.
yes. So it will more more give, it will more detect the light of IR region.
Okay.
So in assignment 3 quiz 2 there's some data is missing, so I have put this data here. So a double heterosection junction indium gallium arsenide phosphide LED emitted as a peak wavelength of 980 nanometer at a dive current of 100 microampere has an internal quantum efficiency of 50% and radiative recombination lifetime of the magnetic carrier in the active region is 60 nanosecond. So the total carrier recombination lifetime in nanosecond. So you have the 5 minute. Please solve it and put your answer on the comment box. And someone can answer me that what is the lifetime, recombination lifetime or carrier lifetime? How can we calculate? Have you know the formula? Jonek already provide a formula of everything.
Uh, so total recombination lifetime is equal to 1 by radiative plus 1 by non-radiative.
Okay. So Jonek is also provide you the internal quantum efficiency formula relation with that no radiative time and non-radiative time also. So please calculate
30 nanoseconds.
30 nanosecond.
30.
Okay, 30. Anyone else? You have 1 tau barabar equal to 1 tau r plus 1 tau nr. You have given internal efficiency also in questions. So you have to calculate this time. Guys, I need the answer. We have to finish on time. Raki Koshik, are you there? Sachin, Sanjeev, Lakshmi, Ladli, Ankush, Namita, you got answer? Namita,
No sir, I'm doing.
Doing, sir.
okay.
Only, sir.
What is? So have you idea to get that answer, na? Everyone can solve this, or you need any help from my side or some? You need if you any clue, then I will give also. Okay, then I will move
Sir,
further.
just
Yes.
30 only, sir.
Okay. So what is the power internet generated within the devices? How much power will be generated? Same data will be same, so you have to calculate the power in that case.
Can you please
Yes.
explain that? Yes, sir. Can you please explain how to solve that numerator, sir?
Which previous one or this one?
Yes, the previous one and this one also. Sir, I'm having some problems while solving the assignment. Yes, I have.
You have already given the internal efficiency equal to 50%. Okay. You have given the value of the TR or equal to radio to recombination type of the minor category is 60 nanosecond. Okay.
Yes.
You know that T equal to TR TNR upon TR plus tau NR. This formula you know that?
Yes, sir.
Okay.
Yes, sir.
So this is a tau. Internal efficiency, you know that how can calculate the internal efficiency? RR
Yes, sir.
upon RR plus RNR, and
R plus R.
RR equal to
Recombination rates.
neta upon T tau R. Okay. From this two, if you solve this equation and these equations, both equations, you give the relationship tau equal to zeta internal into TR. You finally got this equation.
Okay.
So you are given this value, you are given this value. Just you have to multiply, and that you are that total carry recombination lifetime.
Oh, okay, sir. Got it.
So this whole assignment is based on
Yes.
formulas that have been discussed within the class. Okay. So
Okay.
please make make notes and just understand how this formula, all of these fit together.
Okay. Okay.
Because the next few weeks will be like in the similar vein. Okay.
Okay. Okay.
There'll be similar questions.
Okay. Okay.
Please listen.
So I should not provide that formula also, that Jonik.
No, no, formula is fine, but
Okay. Okay. See, the solution will be done by there
students
then.
should have their own cheat sheets. Yeah.
Okay. So next question is the power internal generated within a device. So you have to calculate how much the power will be generated within that LED. So you have to given all the lambda, I, neta internal, and TR. From these four parameter you have to given that power. How much the power consumption of that LED. So you have to calculate that power. So if you have any doubt in this question, then have to ask me. I have to give some hints, or you have to solve that.
63.38, sir.
Okay. So if you have not get this answer, you can comment me on that classroom also, or so I will provide a separate solution, or I will help out that also in that case. Anyone have solved these questions? Or can you provide any?
Yes, sir.
No, no, about so Kusagar, how can you solve this? Can you explain that?
What, sir?
How you solve these questions? Can you give the hint?
Yes, sir. Sir, first we'll find out the rate of charge of carriers by I over Q.
Okay.
Then the energy this is generated with the device, that is h nu into internal quantum efficiency. This will
Okay.
give us the power.
Okay. So if a LED have the internal power is more, this will be good or bad for that optical communication or device for a LED device. It will, how can this quality will be good or bad?
So it is good if the power is more, then it can transmit over long distance. But
No, no,
but we have a
internal generated
when we
power.
increase the power,
Whatever the internally he generated,
no
that
sir,
is.
internally generated power, no sir, internally generated power is not good. Externally generated power is good.
So what happened in that case? How you can optimize that? Any
Sir,
idea
if
about it?
Yes, it will be depend upon the external quantum efficiency.
So
So
what is the
to
external
minimize
and
it,
can you explain the external and internal quantum efficiency difference between both?
external quantum efficiency tells us about that how much power we are getting from the device. Internal quantum efficiency, it tells how the power internally generated within the device.
Within the
More the
device.
internal quantum, yes, more the internal quantum efficiency means that there are more radiative transitions, radiative recombinations are happening. But the power we are getting output, the output we are getting from the device will depend upon the external quantum efficiency. Like the losses which covered like Fresnel reflection loss, TIR loss, absorption loss.
So TR is a loss or that
Total internal reflection will be a loss.
total internal reflection will be loss.
Yes,
But
because
optical fiber is work on only based on the total internal reflection.
that helps in the confinement of the light. Like due to the total internal reflection, the our signal or our wave transmit through the core. But in the light emitting diodes, we want light to be
What light should be?
A.
The total internal reflection is desirable in the fiber, but in the light emitting we actually want to emit the light. So total internal reflection will cause hindrance there.
No, total internal reflection have some loss, but when we have send the signal through the optical fiber, it either be single mode or multi mode. Optical fiber principle is based on the total internal reflection only. We want to reflect that like that. This is the optical fiber, and this is the core cladding. This is the signal we have transmit. So our signal will be retransmit and it will be transmit like that. We do not want that it will be reflected through the cladding. Do not transmit through the transmitter. It whole will be reflected again in the core of the fiber, and this will be get on the output side. If it will be transmitted through the cladding, it will be lost for the some signal will be lost. So anyone else? Anyone can answer this question?
So for the emission devices, we want the light to come out. So without, if we are having TIR in the internal, in the design of the LED, then we won't get any light out. So there will not be that device won't be a useful device. And for the case of this optical fibers, we want maximum light to be travel through the core. So that's why TIR helps in that way.
Okay, okay. So this is the formula through this which you can calculate that power internally generated. And last question is the effective carrier lifetime of a LED is known to be 30 nanosecond. In order to fully support an LED with its best possible bandwidth, the electrical bandwidth of the driver circuit should be at least. So you have to calculate the electrical bandwidth. So in optical fiber there is a two bandwidth, one is electrical bandwidth, one is optical bandwidth. So if we have like that, this is the x and y, and this is our bandwidth formula. So the graph that it is maximum 1, it is root 2 maximum 0.707, and we calculate on the basis of 3 dB of the optical bandwidth or 3 dB of the electrical bandwidth. So this is the electrical bandwidth, and this whole, like from this it will be optical bandwidth. So in optical fiber case we have more optical bandwidth than electrical bandwidth. Okay, this also taught by you ma'am in the class, also in the lectures. So if you have any doubt to how to calculate, or if you have any answer from your audience side, you can tell also me. How can we calculate electrical
I
bandwidth?
have a doubt. So I
Yes.
applied the formula root 3 divided by 2 pi into 30 nanosecond, but I
Okay.
got wrong answer. I applied root 3 divided by 2 pi into tau.
So it is the optical bandwidth, not electrical bandwidth.
So we need to do it
Okay,
by
sir.
using
That's
the
why I got the wrong
formula
answer.
1 by 2 pi tau c, sir.
Yes, yes. This is the electrical bandwidth on 3 dB case. Whatever
Yes,
the
sir.
Namita you told me, that is the optical bandwidth. You calculate that optical bandwidth root 3
Optical
by.
bandwidth. So
That's why the
that's why I got the
that's
wrong
why
answer
it
for
is a
this
more.
question.
That's why it will be greater than optical bandwidth, greater than that electrical bandwidth.
Yes, sir. Yes, sir. That's why I say I got the wrong answer when I
Yes,
filled the assignment.
yes, yes, yes. So you can correct also, that no problem. So you have to
Yes,
make
sir.
out the difference, that whatever the question will be asked about that, because ma'am is also explain both the bandwidth, electrical and bandwidth in their lecture also.
Yes, sir. Yes, sir.
You can see that at transcript in the English, that we have mentioned everything in that transcript also, that how to calculate that. Okay, so you can download that transcript for your reference, and you can read that also, that if you're not able to see the video and that. So in the after the lecture 2, there is a every lecture has the transcript. So if you have any
But
doubt,
there,
then you can ask, and otherwise we have to conclude here. Jonek, it is okay?
yeah, we can show MATLAB a
So I
little
got
bit,
answer A.
maybe next.
Okay,
Okay.
good.
And text transcripts can be found at the bottom section. It's available already. English transcripts you can download for all of the videos. They're not being made available right below the videos. I have talked to the NPTEL team, but it will take some time. But you can still download all the up to week 9. There are transcripts. Others I'm making right now. So like you can go through
So
them
let's say,
like
will
class
you,
notes or book. Okay. Yeah, go ahead.
sir, I have one query. So, will you be able to provide hands-on one or two session on Simulink also? Because I'm not aware of Simulink at all.
We are doing a lot of simulations of like lasers and coherent detection, etc., in our lab, but we don't use too much Simulink actually. It's the base MATLAB that we use.
So actually, sometimes we have to teach in our class. So that's why, sir, I just want if if it is possible, like to have one or two session on Simulink, then it would be good if it is possible.
Okay, we'll try towards the end though, but like there are people in the lab that are good at Simulink. I'll try to contact them. Okay,
Okay, sir.
but
Okay,
I'm
sir.
not promising that. I will show you
Okay, sir.
MATLAB,
Okay.
whatever is useful, but Simulink
Okay,
is
cool.
somewhat limited in FLCT. So I'll talk to ma'am and arrange something.
Okay, sir. Okay, sir. Okay.
Okay.
So Jonek, we can conclude that, or
Yeah, sure. MATLAB we can show a little bit in next week, I guess.
Yes, next week we show you some basic examples. So how can you write the program and how can you save and that run that program in the MATLAB, and how can you analyze the data that this is
So,
okay for that. I think that Jonek.
yeah, and you don't need like too much in-depth knowledge.
Yes,
And to just to get started, you don't need to wait for us. You can also watch YouTube videos. Like you are doing a course on NPTEL, you can of course watch videos on YouTube. So you can get started on your own also. But next week I'll show some basic things, how the whole thing operates.
so if you have any doubt in the class, live session to class or in the lectures, you can post here in the comment or in the Google Classroom also, so we can again take that doubt in next class.
And whenever we have doubts, we will escalate it to ma'am also.
Yes.
So uh, like
Sir, can you
there are
please
few members.
share the Google Classroom code, sir?
Yeah, you can.
No,
You
no.
can. No,
You
ma'am
can
will be
post in
not
the
add in the
discussion
Google
forum
Classroom.
also.
We can forward that, ma'am.
You can post in the discussion forum also. It is in NPTEL right outside. Like, uh, wait, I'm sharing something. I hope my screen is visible.
Yes,
My
sir,
screen
your
is
screen
visible.
is visible to us.
So this ask a question will take you to a Google group. You can post questions. Like, uh, like we will definitely get back to you whenever we can. And if we cannot answer directly, like we will escalate to ma'am, and ma'am will answer. Like, don't worry. This is a good place to be active on. Okay.
Yes, yes. This too for discussion form in that classroom.
Yeah.
So someone asked that how to calculate the slope efficiency. So in that case, like that we have the laser. I think so. We have to plot that output of that power versus input of the power, and through that power we have take that either linear fitting, and through this we in that some, yeah, in the MATLAB you can plot that graph, or origin or Excel you can that plot that graph, that output power of that laser to input power of laser, and through that you can make that linear fitting of that data, and through that interaction that slope you can find that how much the slope that of that, and whatever that slope will become, that you can put that value of the interaction there, and through that you get the efficiency of that. Jonek, I am right?
Yeah. So your optical output power will be something multiplied by current.
Yes.
So slope efficiency is that something,
Yes.
which will encompass h mu by q, internal efficiency, external efficiency.
Yes, like that p out by p in, like that.
So slope efficiency says uh, how much optical power divided by current. So it will give something like watt by ampere kind of a dimension it will have, and it will capture internal efficiency, external efficiency, and also um, h mu by q, that will also contribute.
So now we have concluded on this session now. So if you have any doubt, then you can post on a Google Classroom or that SWAM form, also discussion form, so we can answer on that also immediately, or question that also. Okay,
And
thank you.
and next week's assignment is a little longer. Please get started earlier, okay? Because it's based on laser, so there are a few more questions. Because you need to be comfortable with lasers if you want to work in optics. So it's a bit longer. So start earlier, and we'll meet again on next Tuesday.
Yes, next Tuesday. Please join before the 7 o'clock, so we can conclude on the time on that. Do
Ronak sir,
not wait.
please give me the answer of my question whenever you got time now. Like how much signal, how many signals can be
Okay.
transferred in a single
Sure,
optical fiber?
sure, Namita.
As a reminder, also post in the discussion. It will be a nice place
Okay,
to
sir,
discuss.
I'll definitely. So actually, sir, it is a practical question. Everyone
Yeah,
asks
yeah,
this question.
Sure,
yeah.
sir. We will discuss in
Okay,
the
sir.
next class also. So you can put also that on discussion form, so we can remind, we can remember that you have that.
Okay, sir. Okay, sir.
Okay, Namita.
Okay, sir. Thank you so much, sir. Thank
Okay,
you, sir.
thank you everyone for that.
Thank you, sir. Thank you so much.
Okay, thank you.